Alright, in this video we're going to start section 5.2, and these are the logarithmic functions and their graphs. And today we're going to look at recognizing and evaluating logarithmic functions with base A and graphing those logarithmic functions. And then in later sections we're going to look at recognizing, evaluating, and graphing the natural logarithmic function. And we're also going to use logs functions to model and solve real-life problems. So in a previous section we studied the concepts of inverse functions. Remember, if we square a number and then we square root it, the square and the square root cancel and we're back to where we started. Those are inverse functions. One undoes what the other did. And these logarithmic functions and exponential functions are inverses. So here it says, there you learned that if a function is one-to-one, that is, if the function has the property that no horizontal line intersects the graph of a function more than once, the function must have an inverse. By looking back at the graphs of the exponential functions introduced in the last section, you will see that every function in the form of f of x equals a to the x passes the horizontal line test, and therefore it must have an inverse function. This inverse function is called the logarithmic function with base a. So here in the blue box is our official book definition of a logarithmic function. For x's that are positive, a's that are positive, and such that they're not equal to 1, here's the big part, y equals log base a of f if and only if x equals a to the y power. So these are equivalent statements. Let's see here. When we read this, we read log base a of x. So base a means that is the base of our exponential. Y is what this whole logarithm is equal to, and logs are just another way to write exponents. So what the value of this is really the exponent y. And it's equal to x. So we're sort of just rewriting an exponential in this different form. So the function given by f of x equals log base a of x is called the logarithmic function with base a. And here again in red is how we read that. Log base a of x. The little subscript letter there is our base, and x is our number. So the equations log base a of x and x equals a to the y power are equivalent. You know, we're just scrambling them around a little bit. Again, here's our base a, that becomes a. Y is what we're equal to, that is our exponent, and x is our number. The first equation is in logarithmic form, the second is in exponential form. For example, the logarithmic equation 2 equals log base 3 of 9 can be written in exponential form, 9 equals 3 squared. The exponential equation 5 to the third equals 125 can be written in logarithmic form. Log base 5 of 125 equals 3. When evaluating logarithms, remember that a logarithm is an exponent. This means that log base a of x is the exponent to which a must be raised to obtain x. For instance, log base 2 of 8 equals 3 because 2 must be raised to the third power to equal 8. So in example 1, we're going to use the definition of logarithmic functions to evaluate each logarithm at the indicated value of x. So first here it says f of x equals log base 2 of x, and x is going to equal 32. So what we have is log base 2 of 32 is equal to what? And let's use the letter y, the variable y. So if we rearrange this and put this into exponential form, log base 2, so our base is 2. This whole thing is a logarithm and it's equal to y. And remember, logs are just exponents. So it's 2 to the y power is equal to 32. And in the last section we learned about the one-to-one property, so we could rewrite this. 2 to the y is equal to 2 to the 5th power. 35 is 2 to the 5th. So now that our bases are the same, we know that the exponents are also equal. So here we have y is equal to 5. Alright, let's look at letter B. Log base 3 of x when x equals 1. So we could think about this as y equals log base 3 of 1. Well, log base 3, that means 3 is our base. Our exponent, or our logarithm, is an exponent. 3 to some power y is equal to 1. 3 to what power equals 1? Or, what do we raise 3 to equal 1? Well, anything to the 0 power is equal to 1, so y is equal to 0. In letter C, log base 4 of 2. Y equals log base 4 of 2. So that's saying 4 to what power is equal to 2? What do we do to 2 or 4 to get a value of 2? Well, this is a nice easy one. We're square rooting. If we square root 4, we get 2. So what exponent do we use for square roots? Well, that's half power. Y equals 1/2. 4 to the half power equals 2. And in letter D, now we have a small fraction. Log base 10 of 1/100th is equal to y. So our base is 10. Base 10 raised to some exponent y is equal to 1/100th. Well, let's just concentrate on that 1/100th. 1/100th is 1 over 10 squared. And now I got the base the same, but we're stuck in the denominator. So let's bring that 10 squared up and make that 10 to the negative 2. So now our bases match up. They're both base 10. So we can set the exponents equal. Y equals negative 2. The logarithmic function with base 10 is called the common log function. It's denoted by log base 10, or simply just log, log. On most calculators, our TI-30s, that has the log button. In example 2, we're going to see how to use a calculator to evaluate common logarithmic functions. You'll learn how to use a calculator to calculate logarithms to any base in the next section. So in example 2, we're going to use a calculator to evaluate the given logarithmic function for the given value of x. So our function f of x equals log of x, the log base 10 of x, the common log. And we want to evaluate that when our value is 10. So log of 10. So just on our calculators, we're going to do log of 10, or maybe on the TI-30s, we hit the 10 first and then the log button. If you do it right, you should get a value of 1. And the next one is a fraction, 1/3. We want to do the log of 1/3. So on our calculator, we'll either do 1 divided by 3 and hit equals, and then take the log of that. Or depending on the calculator, you might want to hit log and then do parenthesis 1 divided by 3. If you get the right answer, it should be negative 0.4771213. And the next one is just a decimal, the common log of 2.5. So 2.5 log, and we should get 0.3979400. And let's see what happens when we throw a negative in there, negative 2. So negative 2, hit the log button, error. We cannot put negative numbers into the logarithmic function. And that might become a little more apparent when we start looking at the graphs of some of these logarithms. Here we have some properties of logarithms. Log to any base of 1 is equal to 0. Because if we rewrite it in exponential form, our base is a, here's our exponent, a to the 0 power equals 1. It doesn't matter what we put in for a, anything to the 0 power is 1. So if you see a log base anything of 1, it's automatically going to equal, or of 0 equal to 0, it's automatically going to equal 1. In number 2, log base a of a equals 1. If you see this scenario, the base and the number we're taking the log of are the same, like log base 2 of 2, since this is a base 2 of 2, it's going to equal 1. Or log base 8 of 8, that's also going to equal 1. If the base and the number there match up, the answer is always 1. Log base a of a to the x, and a raised to the exponent, log base a of x, these are both equal to x. Here again, I like to think about it as the base and the number here cancel out, and we're just left with the exponent, which is x. And sort of the same thing here, a raised to the log base a power, that sort of cancels each other out, and we're just left with whatever x is. And we also have a one-to-one property for logs. Log base a of x is equal to log base a of y. Then that tells us that x is equal to y. Because it's the same log base. Log base a, x and y, we can just set x and y equal. Example 3, let's apply some of those properties. So let's see what we have here. Log base 4 of 1. Log base anything of 1 is equal to 0. So this is going to equal 0. And we could think about it as an exponential. Log base 4. Well, the base of our exponential is 4. It's going to equal to 1. What number goes up here? 4 to what power is 1? Well, that's 0. Letter B. Log base square root 7 of the square root of 7. Well, by property number 2, this is equal to 1. Property number 2 is here. Log base a of a equals 1. Here they were both square roots of 7, so that's going to automatically equal 1. And here we have an example of property 3. 6 raised to the power of log base 6 of 20. Well, the 6 log base 6 sort of cancels each other out, and we're just left with the 20. Again, that was property number 3. You can use the one-to-one property, property 4, to solve simple logarithmic equations, as shown in this next example. Well, let's see what we have here. Log base 3 of x is equal to log base 3 of 12. Both of them have log base 3, so that's our one-to-one property. So we can just set x equal to 12. Property 4, the one-to-one property. In the notes, this got deleted out when I printed them up. This problem here is missing. That should equal the log of 3x. So we have the log of 2x plus 1 is equal to the log of 3x. So we have the log and the log are the same. Those are base 10, the common logs. So we can set the 2x plus 1 equal to the 3x. And let's subtract 2x from each side. So we get x equals 1. In letter C, we're also missing part of the notes there. That should be equal to log base 4 of 10. Log base 4, 10. So both sides of the equal sign have log base 4. So we can set the x squared minus 6 equal to 10. And then let's see what would happen here. Let's set it equal to 0 and factor. Subtract 10 from each side. X squared minus 16 equals 0. Well, yeah, that would work. And we could factor this into x plus 4, x minus 4. And when we set each factor equal to 0, we get x equals positive or negative 4. Another way to do this, we could have just added 6 to both sides and got x squared equals 16. And once we had the squared variable, or the squared variable isolated, we could square root both sides. X equals, the square root of 16 is positive or negative 4. Time for some practice problems. In the first one, evaluate the function at the indicated value without a calculator. So rewrite it in exponential form. It should become clear. The next one, we're going to use a calculator to evaluate that, and the value of x round to 3 decimal places, and that's just a common log, log base 10. In the next couple, we're going to use the properties of logarithms to simplify, or the one-to-one property to simplify. So pause the video, try the practice problems, come back and see how you did. Alrighty, let's see what happens here in number 23. Log base 2 of 64, our x value is 64. So this is going to be log base 2 of 64 is equal to some value y. And remember, that's our exponent. Our base is 2. So 2 to what power is equal to 64? Well, we can rewrite 64 as 2 to the 6th power. So y is equal to 6. Number 29. Here we can use a calculator. So what we're looking at is the log, the LOG, the common log of 7/8. Depending on your calculator, you might want to do 7 divided by 8 equals and hit the log key, or depending on the calculator again, maybe LOG, parenthesis, 7 divided by 8, close parenthesis. If you do all your button pushing correctly, you're going to get about negative 0.058. In number 33 here, we have log base 11 of 11 to the 7th power. Well, this is just one of the properties. Log base 11 of 11 sort of cancels out, and we're just left with 7. And for the last one, 1-to-1 property. Log base 5 of a quantity is equal to log base 5 of 6, so we can set those equal. X plus 1 equals 6. Ooh, now the hard part, subtract 1 from each side. X equals 5. And let's see what the homework assignment is for this. We have page 408, 1 to 3, 9, 10, 12, 19 to 22, and 27 to 28. Might look like a little bit. Remember, a lot of it is just going to be simplifying stuff with the those properties.